Okay, so let's get started with some of the basics of structural steel. So steel buildings kind of came about in the, I think, 1920s. One of the first well-known ones was in Chicago. In recent years, the Burj Khalifa in Dubai has kind of grabbed attention as the world's tallest building. I'm not sure if that still stands, but um, steel is a great building material because it's very strong, stiff, light compared to other things for its strength. All right, various codes for the design of steel in the U.S. This AISC 360 is what we'll focus on the most. 341 gives us seismic um, guidelines, and then there's some other things that we use. Here's kind of a basic outline of AISC 360. It's important that you get this book for this class, as it'll flesh out all the notes that I give you. Okay, so we're going to use LRFD. Sometimes it's called strength. LRFD stands for load and resistance factor design. The basic premise of any design method is we have loads or demand and we have capacity. And from a statistical point of view, we want to keep those far enough apart that we don't have failure on a regular basis. Based on the reality of life, there's always overlap between the loads and the strength, but we want to keep that very, very low. So pretty much all we're going to do this semester is calculate the loads, which can relate to, that might be the load applied, and then from there we're going to calculate moment, shear, axial load, deflection, and then we're going to compare that to how strong something is, how stiff it is, etc. All right, in LRFD on the strength side, we have strength reduction factors. So if you remember from the loads, we had factors on our load combinations. So I've pulled up that PowerPoint. So these factors on the LRFD side are to penalize the loads for the load uncertainties. On the strength side, we're going to penalize the material for material uncertainties. And in structural steel, given the uniformity of the steel, these safety factors tend to be pretty high or close to 1. But you'll never have one greater than 1 because that just doesn't make logical sense. Okay, so different types of materials. The major classes are the carbon steels, which are like the A36, high strength, low alloy steels, which are kind of nicer from a property point of view, and then weathering steels where it creates an iron oxide film that reduces the propensity for corrosion. So A36 is common for plate, channel, and angles. A992 is common for wide flange shapes, so that's actually consists of a lot of the steel produced today. And then hollow structural shapes are A500, grade B, although grade C is starting to replace it. A compatibility table like this gives us some guidelines as to what is the common material for a given shape. So if I have a pipe, I come here, the black box tells me A53 is what you typically get, but you cannot get any other shape in A53 because it's truly a pipe spec. Let's say I have wide flange, A992, but I also can get it in A572 and all these other steels. The challenge when you use these gray boxes is the mill runs may be infrequent and it may be quite difficult to get the material in a timely manner. All right, so you can check that out, study these tables a little bit more. Okay, so one of the first principles I want you to understand is material behavior under load. There's two type of classes. One is where the material ruptures without much deformation, and a second where there's a lot of deformation before it ruptures. And this is structural steel. It has a yield curve similar to what's drawn here. All right, another failure mechanism is buckling, where the thickness to length ratios are high enough. Local buckling is what you see in like a can when you crush it, like a Coke can. In a structural member, you may see waviness where the the elements are slender enough that it can't support the loads without losing strength. There's some definitions here you can understand and some limitations of the width to thickness ratio. So for, say, a wide flange, there's going to be a limit for how slender those elements can be, basically the B over T. So width from the center line to the edge divided by thickness has to be less than that in order for it to be to not have local buckling problems. If it does, you can still use them. You just have to reduce the stresses in those members. Fracture toughness is something we don't talk much about in civil structures. It's essentially how much abuse can an element take or a material take. And there tends to be a transition where you go from a thinner material to a thicker. So these drops in the curve are like for foils, so they don't really apply to our world. So you basically have a fracture transition from thin material to thicker material. And this can be a problem if you do your testing like a Sharpie test on a 1/2 inch specimen and you're getting toughness up in this area, and then you have a 4 inch thick base plate, you're not going to have the same material behavior. Okay, kind of in general, there's a decrease as you go from a specimen to a test like a small scale specimen to a mid scale specimen to the full size structure. There is an inherent decrease in strength, stiffness, stability, and toughness. So it's important to understand that if I do a test on a piece of steel in a lab, it may not necessarily correlate to life in the field. However, following the code, that helps us make some connections between these basic lab tests and what happens in reality. All right, fatigue, there's two methods. Damage tolerance is the better way to go. This safe life is BS, so don't use it. And basically, we can use a fracture mechanics based approach to predict life in a part with a crack in it. Okay, so that's the material side. On the shape side, steel comes in a variety of types: wide flange, channel, angle, pipe, tube. Wide flanges are the most common I-shaped member. We use them for beams, columns, braces. And I think rather than talk much about this, I'll let you guys just read most of these. These shapes have section properties, both just geometric properties and then section properties for design. So these tables are in the Still manual. They're also available online. So take a look at all these different shapes, their properties, and start to get familiar with them. Okay, this is the online shape database tool. This will give you some of the properties, but not all of them. Let me pull up another database for you here. Okay, so this Excel file has all of the geometric and section property data for all of the available AISC shapes. And that's given to you here under Files, this path here, and it's this file right here, AISC version 15. Anyway, so I can come in here and say, okay, I'm looking at using a W30 by 132. I want to know the bending strength parameter, 437 inches cubed. So I can use this for design. So if I don't have access to the manual, I can use that. Okay, let's see. Bolts, definitely preferred in the field when you're a long ways away from big cities. There's different types, and we'll get into those extensively later in class. Okay, some example drawings I've thrown into here, and these are actually found in Canvas. So if you come to Course Basics, there's an example calcs and drawings, and you can see different types of drawing examples. This is for a big commercial project, and it may take a minute to load. Okay, so you are welcome to scroll through here and kind of see how drawings get put together. Some notes, some framing plans, and then we get into some elevations. And then later in this set, there's some detail examples of how things are connected together. Anyway, I've given these to you so you can go through and just start to get a feel for how a drawing set looks and gets put together. So different examples, steel building, here's a concrete framing plan, beam schedule in concrete, and a foundation detail. Anyway, so those drawings, there's some of your submittals where you need to include a detail or a plan view of something. And this is a place you can go get some ideas of how they should look. And then as you have questions, which I would fully expect you to have in class, we can discuss things more in detail. All right, I think that's a good introduction for the steel fundamentals. Get into this more, read the sections, kind of thumb through the steel code, get familiar with it, and we shall talk more in class about it.